concept when limit of f of x is a finite value is definition for horizontal asymptotes. So horizontal asymptote. And the other one is the end behavior of the function. Again, all of these studied in pre-calculus, except now you get their definitions. So limit f of x equals to either positive or negative infinity, with the input also positive, negative, infinity, we get the end behavior. So to outline both of these on the single picture, I'm going to use the mighty function called e to the x. So this is f of x equal e to the x function. You all know, you better know, how this looks like, that it goes through 1 and all other cool things. Now, on this end, we have that the limit as x approaches negative infinity of e to the x is equal to 0. That is our horizontal asymptote at y equals 0, x-axis. On this end, we have limit of e to the x is equal to positive infinity. X approaches positive infinity. And that's the end behavior. No asymptotes on that side, vertical or horizontal. It just tells you that as you go forever to the right, you will go forever up. So it grows all the time. So these are two different concepts now. You have the end behavior, which is when you plug in infinity of some kind and you get the infinity of some kind. So for instance, your x squared graph will have end behavior on left and right, both going up to positive infinity. And then you have the horizontal asymptote, which is the finite number that you get. Now, I did briefly mention population model earlier, and I said that something like this would be a bad population model, because you start with having, right, some population at that 1 would be your P0, and the end behavior shows that if you wait forever, you will have infinitely many people or bacteria or rabbits or whatever. You can't have any of that because of the finite space and resources and everything else. So a different population model emerges called logistics model. We're not going to study its formula or anything like that now. We're going to do that later. But I just want to show, because this one on the right-hand side will actually have, again, now we'll have asymptotic behavior, because that behavior now is going to follow this horizontal asymptote, which is known as carrying capacity. See, carrying capacity for our planet is calculated, recalculated again and again, and depending where you read, goes anywhere from 10 billion, and we're almost there, to 15 billion, which is, again, we're almost there. It's exponential growth. So it's minute to 12 either way. So this is much better graph in terms of application for population. The one above could be for something else. Now, generally, right, the other above the graph, right, the e to the x graph, it can generally show a good match for certain time. So if you just look at, a little bit of the graph, it's a good match, but then you have that, happen here as well. So the one below is much better for the application. Now, this is also some type of exponential graph called logistics. We'll see that later in the class. Not today, but down the line. So now, over here, for this point, I get to write limit of a function is equal to L as x goes to infinity. And that's that L. From the first class, we understand the limit as a y value to the problem. We also said that we could possibly think about limits in terms of it's just a solution, right, as you plug in x. But it's just much more powerful way to compute those y values. So every answer that you get on the right-hand side is something that is on the y-axis, whether it's positive infinity, negative infinity, 0, or whatever number along that y-axis. So if we are trying to compare these two problems, we see that for e to the x, we are getting n behavior because it's going to shoot to infinity. Y is going to try to go to infinity. And over here, y is going to try and settle at the L value, right? So that's the idea behind, that's the difference behind the end behavior and the horizontal asymptote. So that's it. Now, the question is, how do you remember anything from your pre-calculus course regarding horizontal asymptotes? You had those rules for rational functions where something with a degree, and then, does anyone remember anything? Yeah? You do remember? Okay, so you're getting there. You can have a slant asymptote as well? Okay. All right, so see? Now, you know what's the good news? If you are freaking out now, you don't need to know it at all. That's the good news, all right? Because now we have the definition we can compute every time. You were forced to memorize that in pre-calculus and use it because you did not have a limit tool to compute it. But now, we have the tool. The rule was, if the numerator, the degree in the numerator is bigger than the denominator, no horizontal asymptote. If they're the same, then the front coefficients are the asymptote. And if the denominator has the bigger exponent, then its asymptote is 0. At 0. So y equals 0. X-axis. And you memorize those rules, and then you use them because in order to sit in Calc1, you had to pass pre-Calc 2, and in order to sit in pre-Calc 2, you had to pass pre-Calc 1, and that stuff was pre-Calc 1. So, right? That's how you use mathematics to make conclusions. But we don't need to know that anymore, because now look what we have. Say the problem says, what's the limit x goes to infinity of x cubed plus 3x squared minus 8 divided by 5x cubed minus 1. Right? Now this question, if you study theorems and definitions, is asking you where is the horizontal asymptote actually, right? Because it's looking what's happening as x goes to infinity. So now all you need to do is to say, well, solve this, and the way you solve it is you divide each term, there are 5 terms there altogether, with the x raised to the highest exponent around. What's the highest exponent around? X to the 3. So you divide by x to the 3 everywhere, x cubed. So you have to remember that. That's what you have to learn. So that's the method. You divide by the highest exponent. Don't forget to copy the limit, or minus 5. And then we have x cubed divided by x cubed is? Great. Then 3 over x, they cancel, and minus 8 over x cubed. Right at the bottom, 5 minus 1 over x cubed. I'm using air quotations now. If I'm to plug in infinity, what happens to 3 pieces of paper as I cut them infinitely many times? They go to nothing, exactly. So 3 pieces of paper will go to nothing. How about 8 pieces of paper cut forever? And here is a single piece of paper cut infinitely many times. Also goes to nothing. What are you left with? 1 over 5. Now, you memorized in pre-Calc1 that if the exponents are the same, and they are, x cubed and x cubed, your horizontal asymptote is where the front coefficients are, which is 1 over 5. So there it is. You don't have to know that anymore because now you have the limit definition, and you can do it. So that's just once. That's efficiency. So horizontal asymptote at y equals 1/5. Again, don't write aj equal 1/5. That makes no sense. It's nothing. Y equals 1/5 is equation.
So the answer right to that should be lim as x approaches infinity to be 1 over 5.
Yes. Oh yeah, also don't write this. That also has no meaning. Or this also has no meaning. Because LIM are just 3 letters that have no meaning. You have to have everything. The notation says limit, you have to have a function or function in terms of values, and then you also have to say where x goes. All of that is the notation. This means nothing, this means nothing. That just, you might as well leave it blank. Same amount of points. There is that all of this is equal to this. And no partial writing of any kind. I told you this limit over here is 5 points worth, all right? You skip it, minus 5. Skip it twice in a problem, minus 10 out of 8 points. So figure out, it's worse than SATs. The stream will not catch the sarcasm and irony in it, but it's okay. Or is it? No one knows. Should we do more problems?
We do one more.
Sure. What are good numbers? 7s and 9s, we didn't use those. Limit x approaches negative infinity of x to the 5 minus 9x plus 3 divided by 4x squared minus 11. Yeah, good enough. You know what to do.
doesn't actually matter if you do the math right, as long as you know an x is underneath something, because no matter what power x is to, it's just gonna disappear, right?
Yeah. My friend just texted me and said that the boss caught her watching the stream at work and asked her if she's gonna do math or work today. And I have a screenshot. People in trouble. Sitting next semester, you're sitting in a different class, watching the stream from this class live in their class. Ooh, okay. Yeah.
I wonder, I was gonna say, doesn't infinity like loop around? Like, yeah, that's the proper face for it. Yeah, when you get like real deep in mathematics, apparently like the infinities loop around and like, you know. I don't know.
How deep do you have to get before that pops up?
Man, you gotta go pretty deep.
Is that Calc1 shit?
That is like down the rabbit hole of the view. Yeah. It's like one of those stone ideas that someone came up with. You know, like someone with like way more money and degrees than you just do the same shit. Yeah, like what is theoretical mathematics? Like you have a board full of everything. It's like, yeah, what's that? Oh, I just wrote it up there. This is how. Well, that's what pisses me off about college is like throughout my math class, I would ask a question, right? And the answer I would get for a lot of questions is, you'll learn that later, or like something like that, right? And it's like, okay, well, somewhere down the line, some dude is just telling me that it's right. So like, how the fuck do I know any of this is actually useful?
Yeah, because pricing is x to the fifth, and we divide everything by x.
There's some weird people out there.
4 divided by x to the fifth is 4 over x to the third. 11 divided by x to the fifth is 4 over x to the fifth. The x is the negative thing. We put negative in all the x's. That becomes a 0 because 1 over infinity is 0. That becomes 0. 0. So 1 minus 0 over 0 over 0 minus 0.
Something that has like no real application to anything. He just made it up like in the lecture.
He's loving it.
Like, man. Yeah, I taught them wrong as a joke. I did 2.3 because I saw the 53 problems at 1 and I was like, yeah, I'll do that later. And about like
Okay, let's take a look at this together.
I'll do this. I'll get on it eventually. Hey, don't the infinities loop around at some point?
Yes.
Did you explain that?
I can. All right. Yes. Yep. All right. So let's solve this problem, and then we're done. And then, yeah. And then next lecture after that, what are we gonna do? So we are going to divide by the highest exponent, which is x to the 5. So there we go, there we go, there we go. And as you cancel, don't forget the limit, 5 points. We have 1 minus 9 over x to the 4th plus 3 over x to the 5 divided by 4 over x to the 3 minus 11 over x to the 5, no sneezing. And this goes to 0, this goes to 0, this goes to 0, this goes, everything went to 0, and we have 1 over 0. Right? Explosion. Therefore, no ha. The definition for the horizontal asymptote clearly states that the horizontal asymptote occurs when the limit is equal to the finite value. That's that part where I said you have to learn before you do homework. Let's say that you picked up in class that you are supposed to divide with the x with the highest exponent, and you solve a problem, and you get 1 over 0. Now what, right? So calculation went well, but the most important thing is to state whether there is or there is not horizontal asymptote, and if there is, where, right? So that will be there. That answer will be there only if you learn the theory, and the theory states if the limit is finite, so if this calculation is 7, let's say, then horizontal asymptote is at 7. If you get 1 over 0, infinity of any kind, you are going to state no horizontal asymptote. Bueno? All right, perfect. Let me just see if we can figure out something else. Any questions, concerns? You guys are awfully quiet. I didn't do that well. I failed this time. It should have sounded like you guys are awfully quiet. There we go. Now I did it well. But I rushed it and I messed it up. Questions, concerns, anything?
Does this one go to infinity or negative infinity?
Irrelevant. Because we are getting no horizontal asymptote on this one. Yes, but if it's end behavior, then it's important, and we are in some cases look at a graph if we have the graph. If we don't have a graph, we have to look at we can compute the value, see whether it's rising or falling. We can do either or. I just want to see if they have any kind of crazy problems that we would have to address. So I'll log in the textbook real quick. So for the textbooks, what I use is this website. They used to be extremely cheap. Now I think they're expensive, but they might still be cheaper than the books, conventional books. It's this vitalsource.com. And they're not only math, they have all kinds of textbooks. This is like United Nations of textbooks. They have everything. Here's the calculus first edition, here's the second one. Come on, don't be afraid. Anytime this week. Maybe if I jump. That worked. All right, so you can see you have the same thing in MyMATLAB. Obviously, you're not going to use it here because you have in MyMATLAB. You have the entire textbook there. Limits at infinity and horizontal. Here is the definition, as you can see, in box. So this is something that you should definitely put on your class preps every time. Anything that is boxed is going to be used heavily. And in some cases, if you don't know it, you can't do the problem at all. So there's the definition for horizontal asymptote. If you get a finite number, that L means finite number, like 7, -10, 1/4, or 0. So anything like that, then the asymptote is at y equals L. And that clearly states there. Then you have a few examples. You know all the letters, so you will read that. Here are the limits saying that going to infinity can go to infinity. Eventually they talk about end behavior. So when you look at the function, you know how it looks like. Here's the end behavior explanation on some kind of x to the 4th. And you see that as you go to negative infinity on x-axis, it goes up to positive infinity, and so on. So all of these things are in the textbook you can read. Here's more on end behavior of the function. Again, look, end behavior of the function, in this case horizontal asymptote, negative infinity and positive infinity, both to 4, which means there's a horizontal asymptote at 4, and the graph has to bend to follow it. Oh, there is another case over here. Or is it? No. Hopefully we'll run into it eventually. We'll definitely run into it in chapter 4. One thing that you should know about horizontal asymptotes is that functions can cut through them. You can cut through slant and horizontal asymptote, but you can't cut through vertical one. And the answer is, and the reason is, the vertical asymptotes are asymptotes whose answers are infinity, where and that's local infinity, where the horizontal asymptotes have to be obeyed at infinities, and then for this space in between, well, you can cut through them. It's okay. Slant asymptote occurs when you do the long division for it. Slant asymptotes occur when you have exponents off by 1. So exponent in the numerator is by 1 larger than exponent in the denominator. And behavior for polynomials and rational functions, talked about all of that stuff. They put that stuff in boxes. And then let's go to homework, see how the homework. Here's the exponential. I talked about e to the x and ln x, so they put that all the way at the end. You can do wonderful stuff with trig functions like tangents and secants and cosecants. Okay, you can look at all of that stuff and understand that before you try some of the problems. Now we did problems, the ones that are in 30s. We did 15 through 24. Whoa, look at the 41 through spicy. All right, so which one don't you like? 41, 42, 43, 44? Pick one. First come, first serve.
43.
43 it is. Sold. All right. I'll write it first and then I'll switch. So, whoa, cube root. We are doomed. So we have, whoa, this is a fun one. So cube root of x to the 6 plus 8. And then we have 4x squared plus square root of 3x to the 4th plus 1. Okay, let's take a look at this together. Now I'm going to ask you, how many terms do you see right off the problem, like that, the top layer of the problem? How many terms do you see? 3. There's the cube root term on top, and then 4x squared term separate from the square root, right? So there are 3 in general, right? Now within some of those you have multiple terms, like, x plus 6 plus 8, that's 2 terms. Okay, so we have these 3. Cool. Now looking at these 3, one at a time, So overall 3. What is the highest exponent? We have one answer that says squared. Anything else? Square's right. Anyone else? Square is right. So what do we actually have? We have x to the 6 cube root, which is also x squared. We have x to the 4th square root, which is also x squared. So technically, all of the leading terms are x squared. All of them. Now we know that we can't take the cube root because of plus 8. We can't take the square root because of plus 1. So we can't compute this right off the bat. But at least you know that all of these are x squared, actually, in general. And you know that we only look at the highest exponents. So what do I divide by? I divide by x squared, and then as x squared undergoes these roots, the exponent will change. So the top one is divided by x squared, but I write the line longer than the root to make sure that you know that the x squared did not go under the root yet. Same thing for the bottom. Now this one is easy over here, right? So now what happens? Oh, I forgot the limit. Let me put the limit in front instead of f of x. Want to play that game? Because I have more points. They're in my sleeves and everything. Remember the card that time? What we did do? He knew he had the red one. All right, so limit x goes to infinity. And now x squared is going to go under the cube root. So now this becomes x to the 6 over x to the 6 plus 8 over x to the 6. This is just 4 when it cancels. And now we have a square root. 3x to the 4 over x to the 4 plus 1 over x to the 4. So this is just algebra. You're doing factoring backwards. Now you're stuffing the square roots. Limit x goes to infinity. We have the cube root of 1 plus 8 over x to the 6. 4 plus, that cube is awful. There we go. Square root of 3 plus 1 over x to the 4th. Now we know that goes to 0, that goes to 0. And look what you got. Cube root of 1 is 1 divided by 4 plus root 3. How awesome is that? Come on. How awesome is that? Amazing, exactly. Beautiful. This could be the problem next time someone tells you, what do you know? Show them this problem. Especially if they go, what do you know? I have kids.
Oh my God.
I know there's a PhD in that. Immediately this problem. Just write it down and ask them to do it. Or I doubt. Just ask them what's the cube root of 8. That should be sufficient. And if they get through that one, you continue. You lead with this then. Right? So lead with cube root of 8 and then transition into this. Okay? Because it also has a cube root. All right. If you want to make this friendlier, right? We are going to get rid of that cube root, sorry, square root of 3 by multiplying, right? Right. Okay. So 16 minus 3 is? Nice. So the answer is, so where is the horizontal asymptote? At 4 minus root 3 over 13. Then ask them to pronounce that. Read it out. Can you just read this? I know 4. Awesome. I just seen this. I just glanced in a book and I've seen this. Amazing. You're not too thrilled. Where would you start? Graphing the normal LNX. And then what we do? Okay, so that's at 1. Actually, I don't need these arrows and stuff. Okay, and what should I do? Yes. So you find what's below x-axis and you push it up. So this is lnx. This one is going to be, so you have that part and then you have the asymptotically, bam, like that. And here's a $1 million question. Can you write this? Can you write the definition? You know how for absolute x you have that it's, I put the integral there. You have that it's x for all x's larger or equal than 0, and then it's negative x for x less than 0. Can you write that for this one? For ln's? So how would that look like for ln? Absolute ln. ln x? Nope. For 1, exactly. This statement says that this is the same as this. That's that statement. Now what do I do for the rest? Yep. For what?
For everything less than, everything less than 1.
Between 0 and 1. 0 less than x less than 1. And that will be the green part.
Oh, yeah, because you can't go past 0.
Yep, can't go there. X's are not defined past 0. That was related to problem 48. Can you take a limit of something like this? The answer is hell no. Can you take limit over here? Yes, right? Because you take each line separately. So when you have these piecewise functions, each piece is the separate line, like separate item, and then you take limit separately. So you can't take the limit of this, but you can take limit of these two separate, like that. So this was a little exercise in how to deal with these absolute values, so you don't freak out, not if, but when you see them on homework and floating around. Awesome. That was a good thing. I'm just pushing it now. How about that one? Is anyone crying for the calculator now?
LN, except it doesn't have the tail, like that bottom tail on it. Like just
He does have a tail on it. That's what it is. Because absolute value now allows for negative numbers as well. Cool? All right. Well, let's say bye to the stream, and we'll restart for 2.6 at some point. Bye, stream.